Hi, and welcome to our next installment of your Momentum Unit 6 notes titled Collisions and the Law of Conservation of Momentum. I'll take a moment to get my sound adjusted because people complained about the last set of notes, so hopefully this is better. Okay, so as you flip over your note helper, if you stapled it the way that I talked about in class, then you'll find on the back page where we start off with the title, Notes, Collisions, and the Law of Conservation of Momentum. The first thing that we want to address is going to be that box titled Law of Conservation of Momentum. Here is what it states. Momentum lost by one object must be equal to the momentum gained by another. We've discussed the law of conservation of mass before, the law of conservation of energy. Whenever we have something conserved, the question always comes up from students, what does conserved mean? That means that we have things remain the same. Remain the same or equal. There's your keyword underlined in the phrase. The equation that you can copy down on the line below that is that whenever you have the initial momentum, mass times velocity, it shall be equal to the final momentum, mass times velocity. That's going to be the totals, which are equal to each other. Total initial momentum and total final momentum shall be the same. You'll find that sometimes the numbers are distributed in different ways, but the total will remain the same from beginning to end. So now we like to discuss collisions, and one of your primary tasks is going to be to read a scenario and first determine what type of collision it is. So as you look at the bottom of your notes, it gives you 3 basic collisions, and once you determine what type of collision we're talking about, then you can apply the appropriate formula as it appears on your notes. So with these problems, the first battle is going to be by reading the scenario to figure out which type of collision. And then once you've done that, then to do the math correctly is the second half of the battle. Let's introduce the first type of collision. Elastic collisions occur when objects bounce off of each other. Elastic collisions occur when objects bounce off of each other. You'll have a collision and they do not stick together. They remain separate entities, and this little animation that's going shows just that. They're colliding with each other, but as they collide with each other, each one of those different dots, they don't stick to the other one. They're going to bounce off and keep moving. With elastic collisions, and the same will be true with all of our other types of collisions, you can answer that yes, total momentum is conserved. Total momentum and total energy, for that matter, will be conserved. That's a law. Momentum is going to be conserved no matter what type of collision you have. Look for that to be an item that's going to be tested and quizzed. Is momentum conserved in all these types of collisions? Yes, for all of them. You can fill in the next box for the equations. So now we separate into 2 equations that we can apply to elastic collisions. The first equation we use when the initial momentum of one object is 0, then this equation you should fill in the box. Momentum of object 1 is equal to momentum of object 2. Pretty basic equivalency there. The next box underneath that says when both objects have some initial momentum, we'll stretch this out and say in the beginning the 2 objects have their own momentum and they're separate. In the end, the 2 objects will have their own momentum and be still separate from each other. They do not combine together. An elastic collision keeps those objects that are colliding as 2 separate entities before and after the collision. Next example. So now we have to get crafty, and I want you to flip to the class practice page of the notes, and this is where we're going to kind of hop over and do the examples for elastic collisions. That first example under class practice applies to elastic collisions, so if you want to label it as such, please do so now. And it reads as follows. A blue train car with a mass of 1 kilogram and a velocity of 2 meters per second collides elastically with a stationary green train car with a mass of 1 kilogram. What's the velocity of the green car after the collision? Here you can see the visual of what we just described in the question blue train car is going to move forward, collide with this green car, which is initially stationary, and we want to figure out how fast this will move away. Conceptually, this is a very easy problem. Since they have the same mass, what you're going to look for is an exchange of velocity. This only occurs when they have the same mass. So initially, you can see here, if you follow my pointer, this car has a mass of 1, this car has a mass of 1. Since that is the case, they're just going to switch velocities, an exchange of velocity. If this one is going 2 meters per second in the beginning, once they collide, it will transfer its momentum to the object of equal size, and now green train car is going to move off at, you guessed it, 2 meters per second. Mathematically, here's how we would support that conceptual idea. Since one car is not moving in the beginning, that's what stationary means, we're going to use that first equation that we talked about underneath the box titled elastic collisions. M1v1 is equal to M2v2. The mass of train car, the blue one, is 1. The velocity is 2, as it says here on the picture and also in the words. The mass of object 2, that's the green train car, still mass of 1, and the velocity, we don't know. We're going to figure it out. Mathematically, you'll see it supports the concept I just talked about. So when I multiply this together on the left-hand side, 1 times 2 is definitely 2, and that's equal to the second velocity. So now we have a second problem associated with this same scenario, and we'll go on to say, well, what if the masses are different? So now we're going to pretend that the blue train car is still 1, but the green train car is bigger. It now has a mass of 2 kilograms. So if you're thinking about this conceptually, when you have this blue car moving with a certain momentum, in this case 2 kilograms meters per second, when you transfer that momentum to a larger object, is it going to move away at the same velocity, greater velocity, or smaller velocity? If you're a conceptual thinker, you would have answered that when this momentum of the smaller object transfers to the momentum of the bigger object, it's going to cause that bigger object to move away more slowly. Let's figure out how much slower it will move away. So since we're still dealing with one object that was stationary in the beginning, we're going to continue with the same equation for an elastic collision in which one object is stationary in the beginning. M1v1 is equal to M2v2. We're going to plug in the mass of the blue car, that's object 1, and the velocity of it. In the beginning, the mass is 1, the velocity is still 2. That goes on the left-hand side underneath. But now with the green train car, the mass of object 2, the green car, it's now 2 kilograms, and we're going to figure out the velocity. Here's how it would look mathematically. So when we simplify this down, 2 times 1 is definitely 2, and it's equal to 2 times velocity of object 2. When you divide that out, you find out that, yes, it's going to move away half as slow because it's twice as big. Again, recap, when this object is twice as big and the momentum from the smaller object is transferred to it, it's going to move away half as slow. All right, so the next topic is, what do we do if both objects have initial velocity? So let's continue on with the next bit of class practice. The blue train car now has a mass of 1 and a velocity of 2, and the green train car is no longer stationary. It has an initial velocity of 1 meter per second. So let's go flip over to our notes on the front page, and let's pull in the equation for what do we do when these cars are both moving in the beginning. There's the equation you wrote down. Go ahead and take a moment to copy it in. Pause the notes if you need to. Once we've written the bare equation, we can substitute in the numbers. We called the blue train car object 1 just because it appears in the picture first. There's no real reason why. But let's plug in the mass and velocity of the blue train car. The problem stated that the mass was 1, velocity is 2, so we're going to put it underneath here. For the green train car, in the beginning, the mass is 1 and its velocity is 1. So there's what we have in the initial scenario. In the final scenario, once they've collided, Mass is not going to change because of the collision. We don't have parts falling off. They're definitely not sticking together to increase the mass. So mass is still 1 kilogram of that blue car. The new velocity, it tells us in the problem, after the collision, the blue car has a velocity of 1, so I put that here. And we want to know what the velocity is of the green train car in this final scenario post-collision. Again, mass of the green car still remains the same. The mass does not change from beginning boop, to end. So let's simplify this down. 2 plus 1 is 3. On the right hand side of the equal sign, we get 1 times 1, that's here, plus the V2. To simplify this down, we'll subtract 1 from both sides, and we end up with the second velocity is 2 meters per second. Again, the concept here is that, if you were wondering why we went through all of that, to prove it mathematically, everyone doesn't get the concept initially, but now that we've done that, we can say the concept is when they are the same mass, what happens with velocity? They swap velocities when they are the same mass. Huge concept. Try to keep that with you. You're going to be assessed on it. Be able to answer either through mathematical calculations or through the conceptual reasoning. Same mass, they'll switch velocities. All right, flip back to the title page for collisions notes, and now we're going to fill in the inelastic collision definition. As the term inelastic implies, objects will stick together when they collide. Total momentum, yes, is definitely conserved, so you can answer yes to that question. And here's what the equation would look like for an inelastic collision. Take a moment, pause the lecture if necessary to fill that equation in the box in its entirety. Once you're done with that, let's flip back to the class practice and see how to approach these inelastic examples. So the first example for an inelastic collision is we have this blue sphere and a red sphere, and before the collision they're both independent, moving with some velocity. And after the collision you can tell, yep, they've stuck together and now they're moving away with a single velocity. They're moving away as a unit, stuck together. What's the velocity of these two objects as they move away after the collision? So if we pull in our inelastic collision example, we're going to use the red sphere as object 1, just because it appears first in the picture, and plug in the mass and velocity underneath object 1's momentum. Let's see if I can pencil this in. Mass is 4, velocity is 6. That's supposed to be a parentheses. Yeah, this isn't working out nicely, but we'll go with it. Plus object 2, the mass is 2, and notice the sign of the velocity. That's important to us because you see it moving left, you see the negative sign, it all should make sense. They support each other. So the velocity of object 2 in the initial scenario is -4. Equal to, in the final scenario, they are stuck together as one unit. So let's add these masses together. Object 1 had a mass of 4, plus object 2 is now with it. It had a mass of 2. And we want to find out the new velocity of that unit created by the inelastic collision. Okay, so what is this? 24 plus -8. Those signs are super important when it comes to momentum because it is a vector quantity and the sign matters. And now we have it equal to 6 times VF. Adding these together, the 24 plus the -8 gives you 16. And it's equal to, nothing has changed on the right side, so we're going to just drop down and recopy 6 times VF. When you divide that out, you should definitely get that the final velocity of that unit together is 2.67